You ever wonder what the circulatory system of a modern building really looks like? I mean, it's not just wires and concrete. There's this whole hidden network of pipes and pumps, this powerful current silently moving energy around to keep everything and everyone comfortable. Today, we're going to pull back the curtain on that hidden world.
So, how do you do it? How do you bring a massive skyscraper to life? We're not just talking about plugging in a big air conditioner here. This is a massive feat of engineering that demands incredible precision, a ton of power, and, a really deep understanding of physics. All right, let's dive into this masterclass and see how it's done, step by step. All right, so here's our roadmap for this journey. First, we're going to start at the very heart of the system, where all that cooling power is actually created. Then, we'll follow that cool water through the building's arteries, see how it actually delivers comfort. And finally, we'll get to the really intense part, the rigorous testing that proves the whole thing works.
Every great journey has to start somewhere. And for a chilled water system, that starting point is the plant room. This is where massive machines perform what is basically modern alchemy, turning raw electricity into pure cooling cold. This is where it all begins.
Okay, before we get our hands dirty, we got to speak the language. And the most fundamental unit we have is the ton of refrigeration, or TR. It's such a cool, kind of old-school term, but it perfectly captures what we're doing. We're removing enough heat from a space to melt a literal ton of ice. This is how we measure the raw, brute force power of our system.
So, let's break down just how precise you have to be to install one of these chiller units. Look at this sequence. Step 1 is all about space. That 1.5 meters of clearance? Yeah, that's not a friendly suggestion. It's a hard requirement from codes like ASHRAE 90.1, so people can actually service the thing safely. Then step 2, the isolation. This is absolutely crucial. That huge concrete inertia pad and the spring isolators underneath it, they absorb the machine's vibration so the entire building doesn't have a constant, annoying hum. Only after that's perfect do you move to step 3 and connect the main pipes. And finally, you get to steps 4 and 5, which are all about checking your work and hooking it up to the building's brain, making sure it's hitting its temperature targets and communicating properly. You have to get this sequence exactly right. There's no other way. So you run the math for a pretty standard 300-ton system, and what do you get? You get this number, 720 gallons per minute. Let me put that in perspective for you. That's like filling up 14 bathtubs with water every single minute. That's the sheer volume of water this machine is constantly circulating. It just shows you the incredible scale of the energy that we're moving around. So a chiller is great at making water cold, but it can't make it move. For that, you need muscle. You need a powerful heartbeat to push all that cooling energy through the veins of the building. For that, you need a pump room.
Welcome to the engine room. Looking at the steps, first you install 2 sets of pumps, the primary pumps, which just loop water through the chiller, and the big secondary pumps, which are the ones that send it out into the building. Step 2 is connecting the headers. You can think of those as big traffic circles for water. But step 3 is where the magic is. See those gray boxes, the VFDs? Those are variable frequency drives. They're like a super smart gas pedal for the pumps, adjusting their speed in real time to match exactly what the building needs. It saves an unbelievable amount of energy. Steps 4 and 5 are just adding the essential safety gear and, of course, the power to make it all go. And just like that, the system has its heartbeat.
So, we've generated our cold and we've got the pumps to move it. Now, the big question, how do we get it from the basement all the way up to a penthouse office on the 50th floor? Well, we build the system's arteries, the distribution network.
You can really think about the piping installation as a journey in itself. It starts with incredibly precise welding down in the plant room. Then, as the pipes snake their way up through the building, you've got these heavy-duty supports going in every 3 to 4 meters to handle the immense weight. After that comes the really critical 1.5-inch insulation wrap, which keeps the water ice cold on its trip. And finally, everything gets tagged and tested. Every single step has to follow strict industry standards, like the ones from SMACNA.
Okay, now here's a detail that seems incredibly tiny, but trust me, it is a game changer. Every single horizontal pipe has to be installed with a slope. We're talking a 1 to 500 slope. It's almost impossible to see with your own eyes, but that tiny incline lets air, which is the absolute enemy of a water system, get pushed out properly. If you install the pipes perfectly flat, you trap air bubbles, and that leads to gurgling noises, corrosion, and just awful performance. So the lesson here is simple. Gravity is your best friend. Use it.
Think of these as the vital signs of a healthy pipe network. Engineers are aiming for a water velocity between 4 and 6 feet per second. See, if it's too slow, it's inefficient. But if it's too fast, it literally starts eating away at the inside of the pipes. They also have to calculate how much pressure is lost over distance to make sure the pumps are the right size. And all along the way, you have these key components: strainers, valves, sensors that keep the system clean, balanced, and healthy for decades.
All right, so our chilled water has been created, and it's traveled hundreds of meters through the building. We are now at the finish line. This is the moment where the magic really happens, where that cold water finally meets the air to deliver actual comfort to the people inside. So you've basically got three main players that get this job done. For your huge open spaces, like atriums and lobbies, you've got the big guy, the Air Handling Unit, or AHU. To bring in fresh, clean, outside air without wasting energy, you use an Energy Recovery Unit, or ERU, and for all the individual offices and smaller rooms, you have these compact little guys called Fan Coil Units, or FCUs. Each one has a very specific job to do.
Installing a big AHU follows another really strict checklist. Again, step 1 is all about clearance, giving a full meter of space to work on it. Step 2 is connecting the massive air arteries, the supply, return, and fresh air ducts. Step 3, we finally connect our chilled water pipes to the cooling coil inside. But I want you to pay extra close attention to step 4. When air cools down, you get condensation, a lot of it. A drain pan with a strict 1% slope is non-negotiable. It's required by code to get that water away safely, because if you don't, you're asking for leaks, mold, and catastrophic damage. Finally, you test the airflow, the CFM, to prove it's delivering exactly what it's supposed to. This chart shows a really important concept called air balancing. The air being pumped into a room isn't just the same old air getting cooled over and over. It's more like a recipe. In this case, we're taking 10,800 cubic feet per minute of air from the room. We're mixing it with 1,200 CFM of fresh outside air, and that gives us our total supply of 12,000 CFM. This balancing act is what keeps the air from getting stale and meets critical ventilation codes like ASHRAE 62.1.
Now for the smaller FCUs, the big challenge with these is that they're tucked away inside a crowded ceiling, so the installation has to be absolutely perfect from the get-go. After it's mounted, all those connections, the pipes, and especially that all-important slope drain pan have to be triple-checked, because once that ceiling is closed up, they are a real pain to get to. And notice step 4. There's a very specific rule that the flexible ducts can't be longer than 1.5 meters. Any longer than that, and you lose way too much air pressure from friction, basically starving the room of cool air. It's these tiny details that make or break the system.
So the chillers are humming, the pumps are pumping, the fans are blowing. You'd think we're done, right? Nope, not even close. Building the system is one thing, that's the theory. The final, and honestly the most critical act, is proving that it all works exactly as it was designed to. This is system verification.
I just love this quote because it gets to the absolute heart of great engineering. You can have the best plans in the world, the most skilled team putting it all together, but until you put that system under intense pressure and actually measure its performance, it's all just theory. Now comes the proof. So, for starters, the entire massive network of pipes is filled with water and then pressurized to at least 200 pounds per square inch. To give you an idea, that's more than 6 times the pressure you have in your car tires. The system has to hold that insane pressure, usually for a full 24 hours without a single drop leaking from any of the thousands of joints. It is the ultimate stress test.
After it survives the pressure test, the system has to run what we call the commissioning gauntlet. You can see the steps here. First, that hydro test. Then we do a full chemical flush to get rid of any grime or metal shavings left over from construction. Then, in steps 3 and 4, a team of specialists comes in to do what's called TAB, testing, adjusting, and balancing. They fine-tune the system so that every single room gets the exact amount of air and water it was designed for. And finally, every last sensor and valve is calibrated so it reports accurate data to the building's central computer brain, the BMS.
A project is only officially done when this package is handed over. And this is way more than just a stack of paper. It's the building's official birth certificate. It has the final as-built drawings, the owner's manuals for every single piece of equipment, and most importantly, the signed test reports that serve as cold, hard proof that the system is performing exactly as promised.
And just like that, this hidden circulatory system comes roaring to life, a silent testament to some incredible engineering. It delivers perfect comfort on day 1. But the real question, the one we're left with, isn't just about today. It's about how these incredibly complex, energy-hungry systems are going to evolve and adapt to meet the demands of a changing world, to make sure they're not just powerful, but truly sustainable for our future.